So today we will discuss about recurrent neural network. Let me share my slides. Can you see my slides?
Yes, ma'am.
So, first, so you have already looked at different architectures of multi-layered neural networks, deep neural networks, specifically convolutional neural networks, and different architectures involving CNNs, right? So can you tell me what is the main feature of CNN which distinguishes it from a general deep or multi-layer neural network? What is distinguishing about CNN?
Convolution operation.
Yes. So what does it, what is the main thing that it handles? What is it and how? Yes, convolution, definitely. That is in the name. So how is it different? How is a convolutional layer different from a normal, fully connected layer? Yes, Jayachandra? How is a convolution layer different from a fully connected layer? So please answer, otherwise we'll not be able to proceed.
Sir, ma'am, here we have kernels. There in normal neural network we have hidden layers. Here we have hidden layers with kernels.
Yes, it has a kernel, but how is it different from a fully connected layer? How is a convolution kernel different from a fully connected layer?
Ma'am, it is a translation invariant.
It is?
Translation invariant.
It is,
Like,
but why? What is it? How is it translation invariant? So what is its feature?
It is extracting the correlation between the pixels.
It is extracting the correlation
between the pixels which are adjacent pixels.
Between adjacent units, but so can a fully connected layer. Fully connected layer has additional, fully connected layer has all the connections in the convolution plus other connections. So fully connected layer also you are looking at all the neighboring pixels. I mean, how is it different?
The convolution operation uses the convolution operation that is different from multiplication.
That is the definition. So convolution operation is same as, what does convolution operation do? It's a multiplication and addition. Even a fully connected layer does multiplication and addition.
But ma'am, the kernel size is not the same as that in the fully connected one. It is different, and it basically extract.
That is what I'm asking. So please explain, how is it different? And how does
the number of parameters in a convolution layer, convolution neural network is
number of parameters is less?
Yes.
Why is it less?
Because every node in fully connected layer, like every node is connected to the other node in the other node in the other layer, but in convolution neural layers, all the nodes are not connected to all the nodes in the other layer. Only
so it's only sparsely connected, right?
Yes.
Is that
yes.
or is something else? So suppose there are 1,000 nodes in one layer and 1,000 nodes in the second layer. In a fully connected layer, you will require 1,000 by 1,000. Okay. So suppose you have, this is one layer containing 1,000 units, and then the next layer also contains 1,000 units. The parameters in a fully connected layer or a dense layer is 1,000 into 1,000, if we ignore the biases, right? So you are saying that one node is connected to only its neighbors. Suppose there are 3 neighbors, right? So can you say that the number of parameters is 1000 into 3?
Yes.
Is it? Please think. How many parameters are there? If we have a convolution layer with a kernel size of 3.
We should also add the bias.
Ignoring the bias, as I said, suppose there's no bias. I mean, just for simplification. So who can tell me how many parameters are there? Do you all agree that the number of parameters is 3 into 1000?
Oh my.
And what is the number of parameters?
3.
Satyaprakash, what is the number of parameters?
I am 9.
9. How do you get 9?
It's a 3 by 3 kernel, so only 9 parameters.
3 by 3. Where is 3 by 3? So we have 1000 nodes. Each node has 3 neighbors. So where do you get, 3 by 3? Satyaprakash?
Ma'am, I am like saying about the convolution kernel.
Yeah, I am also talking about a convolution kernel. But my depth is 1. There is only 1 layer. There is no, 2 layers, 3 layers. I have a single dimensional input. This is my hidden layer or this is my input layer, which has 1000.
Why would the next layer would have 1000 nodes? It would be lesser than 1000, right?
Suppose I want 1000 nodes.
But then we have to do some padding to the input.
Okay, I will do some padding to have 1000 nodes. Right?
Yeah.
If I have 1000 nodes in the next layer, this is what my, enough dense connection. We have 1000 by 1000 parameters plus 1000 for bias. Okay, so 1 million and 1000. Now, if we have a convolution kernel of size 3, then how many parameters are there? I mean, if you don't do padding, it will be 998. If you do padding, it will be 1000. I'm just trying to make things simple for you. I want to know the number of parameters.
Then 3 into 1000 into 998.
3 into 1000 I've already written, but I'm not satisfied with the answer. I've written 3 into 1000, I've written 9. Do you have any other answer?
3 into 1000 into 998.
3 into 1000 into?
998.
3 into 1000 into 998. This is the third answer. Any other answer? I'm not satisfied with any of these 3 answers.
Ma'am, 3.
Fourth answer is 3. Can you explain?
Same thing like the way the kernel works in the 2D case. This is a 1D case, and only the neighbors are there are just 3 neighbors.
Right.
Effectively
So
to look at.
each node has 3 neighbors. This node also has 3 neighbors. Right? But why is it not 3 into 1000? Can you explain? Every node has 3
Because
neighbors.
I think, yeah, because that's the beauty of convolutional thing, right? I mean,
That's a beauty, but can you explain? Can you tell me
okay.
why is it not 3 into 1000 but 3?
Because the pattern that you're looking at across all these groups of sets of 3.
Because the parameters are shared. Please answer to the point.
Yes,
so
the parameters.
The number of connections is 3 into 1000. So you are right. This is the number of connections. Okay. But the number of parameters is 3 only. Plus 1 for bias. And these parameters are shared. So same parameters W1, W2, W3 is used here, here, here. Okay. So the key word that I was looking for is that the parameters are shared. So there are two things. One is sparsity of connections. Number two, parameters are shared. This is the key factor about a convolution kernel. Do you all agree?
Yes, ma'am.
So I think this is something you must get very clear. While you do many advanced things, the simple things you should get very, very clear. Okay. So anybody has any confusion, please tell me. Or if you don't agree with me also, please tell me. Otherwise, say yes. Is it okay?
Yes, ma'am.
Yes, yes.
Yes, ma'am.
Everybody? Now we will today look at another architecture of deep neural network, or another architecture of neural network called RNN. And what is RNN useful for? RNN is useful for modeling sequences. Now, sequences, there are many data where we have sequences. Like in sentences, we have sequence of words. In speech, we have acoustic features at different time steps. Then video, we have sequence of images. Then we have rainfall measurement, sequence, stock market, daily values of some particular stock, or the minute-wise value. They all form a sequence. Okay, a sequence can be a temporal sequence or a spatial sequence. It is a sequence. Okay. The second characteristic of RNN is that RNN can model variable sized input. Suppose you have some data. Suppose your input is a sentence. So you have 4-word sentences, you have 3-word sentences, you have 5-word sentences, you have 45-word sentences, right? So different sentences can have varying length. Okay. And some example tasks is, suppose given a sentence, you want to classify the sentiment of the sentence. The sentence can be of varying length. A sentence is a sequence of words. Or given a sound signal, you want to recognize what is the phoneme. Or given a video, want to find out what activity is going on. Okay, these are examples of sequences, and these sequences can have varying size. Now, I want to ask you one question. Suppose you are using a convolution network, right? So can you deal with, let us say you are dealing with images. You can, convolution is not restricted to images, right? Convolution can be used whenever there is some spatial sequence. It can be 1D, 2D, 3D, 4D, etc. Okay, convolution can even be applied to sentences. Now tell me, if you are using a convolution network, a convolution layer, can you work with variable size input? Suppose you have some 200 by 200 images, some 1000 by 1000 images. Can you apply the same convolution network to variable size images?
Yes, ma'am, we can apply it.
Good. Why?
And because it is not dependent on how the connections are made, it just captures the surrounding.
Because you have the kernel which is shared. So
Yes, ma'am.
that kernel you can apply to any size of image, right? Only the number of applications will be more. The reason you can do it because the parameters are shared. Okay. Everybody agrees to this?
Yes.
Now these are some examples of where we want to need to look at sequential data. So you want to sample data sequence from a distribution. We want to, given an image, we want to generate a description of an image, textual description of an image, right? Then activity recognition from a video sequence, speech recognition, machine translation, which is taking a sentence in one language and translating it into another language. For example, Hindi to English. Now, just like we discussed that CNN shares parameters, RNN also has a mechanism of sharing parameters. Because we said RNN can work with variable length sequence, this can only happen if parameters are shared. So RNN share weights across multiple layers. For example, suppose this is a sequence. X1 is a vector, it is a sequence and it has components X11, X12, X13, X14, right? And in RNN, we have these layers. So we can call it this is A1, in a gen A1 is the output here. We have A2, A3, A4, or we can refer to them as hidden states H1, H2, H3, H4, etc. And we have parameters. Where are the parameters? Parameters are wherever we have connections. So, so we have some parameters here, right? W1, W2, W3, W4. These are some parameters which go from the input to this layer. Okay. Now, if we want to deal with variable length sequences, we must have all these parameters equal. Okay. So we will share these parameters. Similarly, we have parameters here, 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 here. So we will share these parameters. So we share parameters across time steps in a recurrent neural network. Is this okay? Okay with everybody?
Please
Ma'am, what do you
repeat.
mean when you say that we share it across different timestamps?
Share the parameters. So let us go back to CNN. In CNN, what you have, because you are more comfortable with image, let me take an image example. So you have a 3x3 kernel. So there are 9 parameters plus 1 for bias. So these 10 parameters are used at this position as well as this position. So when it is used at this position, when you are doing back propagation, at this position, these parameters are updated, right? But these parameters and these parameters, they share the parameters. So when it is getting updated, this is also getting updated. Okay. So if there is a W1 here and a W1 here, they're the same W1. Okay. So similarly, if we have a parameter theta here, the same parameter will be here, 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 here. So when we are doing back propagation, when this parameter is getting updated, they are in their common memory, common cell, right? They are not different entities. This is the common entity. When it is changed, it is changed everywhere. Is that okay, or still you don't understand?
Ma'am, it's okay. Is it like that when we use rotational, the orientation pooling, and we only store one of the weights and all the other weights are derived?
No, I don't talk about pooling, etc. Nothing. This is a fundamental thing. Rotation, we are not talking about rotation. We are saying that what is a variable? You work with computer programs. You have a variable, right?
Yes, ma'am.
Suppose X is a variable. Now this X variable, you can use it at different parts of the program.
Yes, ma'am.
So suppose you say X equal to X plus 1. In some other line, you say X equal to X plus Y. So when you're saying X equal to X plus 1, so for X, there is a single memory cell. Okay. So suppose initially X was 5. Now this memory cell will be updated to 6. When you say X equal to X plus Y, suppose Y is 4. So then this will become 10. When it is 10, this X is the same X.
Yes, ma'am.
So how do we use the parameters in a neural network? We have parameters and the parameters have some value at the current time. We do back propagation, we update the value. Okay. So in a convolution kernel, if we have a parameter W1, that W1 is getting updated, and this the same W1 is being used at another position. So when we are doing, suppose we have a loss here, suppose we are back propagating, and we are updating a theta here, right? Now the same theta occurs here, 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 here. So when we are changing theta, this change, that means this parameter in this connection, all these parameters are changing because they're in the same memory cell. Shivam,
Yes, ma'am, it's
do
clear.
you understand or do you still have some confusion?
Ma'am, I have some doubts regarding how do we implement it, but I guess it will be clear once you explain it.
I will want to make it clear now. How do we implement it? By putting it as a single variable.
No, ma'am, that part is clear. That part is clear. I have a doubt regarding how are these weights all equal? Then W1
How
equal
are the
to.
weights are equal? Because of the same weight. Because this is the same variable. As I said, X is one variable. So theta is one variable.
Okay.
It has a single memory, it is the same variable.
No, ma'am, the variable part is clear, but
The
if
same thing, all the parameters are variables, right?
yes, ma'am.
They are there in memory, they are in some portion of memory. When you change it, it changes. So theta is there. This is your computer memory. Look at the first year PDS class. Okay? So theta is there here. Okay. So when you change theta, suppose initially theta was 0.1. Now you change theta, it becomes 0.12. Okay. Now when you come here, you want to update, already it's 0.12, then it gets changed to 0.119. So the same parameter is there in all these cases. It's being used. Shivam?
Yes, ma'am.
I mean, is it clear?
Yes, ma'am, it's clear.
Implementation means it is assigned one memory.
Okay, ma'am.
If it is different, they have different memory allocations. Okay, it is the same variable which we are referring to. Do you understand? So when it's a convolution kernel, the same kernel is shared across various locations. Then there is an RNN. Across time steps, we share parameters. Share means they have the common memory location. Is this clear to everybody?
Yes,
If it is
ma'am.
not clear, please ask.
Yes, ma'am.
So as I was saying, so these are the parameters. There are parameters from connections and they share. So if we say WL is the connection from AL minus 1 to AL, then we say WLI and WLJ are equal for all ij. That is, we can say this is, if we say this is W prime, this is the same W prime, same W prime. And suppose this W prime has 1000 parameters. So there will be 1000 memory locations, W1 to W1000. And the same 1000 parameters are used at different time steps. Okay. Also, there may be parameters here, say W. The same W is being used here. All right. And the advantage is this. We can then have variable length network. If we had a different parameter at every layer, then if it is a sequence of length 3, we will require 3 weight matrices, 3 sets of weight matrices. If it was a sequence of length 300, we will require 300 sets of weight matrices. And all these weights for layer 1, layer 2, layer 3, layer 300, all these weights are distinct. So we will require many examples to learn these parameters. And the number of parameters will be very large. But if we try to think that the dynamics of going from one time step to another is similar, then we use the same set of parameters to show how it changes with time. It is the same thing as you do in CNN. CNN, as you said, all this rotation, invariant. Basically, what you are saying is that it's spatially invariant features. So whether it is a circle in the image, whether the circle is here or here or here, the circle detector, the same set of parameters can be applied in these positions. Similarly, here we are saying we are looking at temporally, we are looking at the sequence, we are looking at the same dynamics across different positions in the sequence.
Hello, ma'am.
Yeah.
Here, what is the significance of a to the power L equals to 0?
So here we are saying that we have a common parameters which take input. We are saying that this is A1, this is A2, this is A3, this is A4. And this size we take as A0. So A0 has some initial values. We can initialize it to 0, 0, 0. Is it okay? Because we consider each of the blocks as similar, which takes input. AI takes input from AI minus 1 and xi1. Okay. So this A1 takes an input from A0 and x1. And A0 we can take
What
as.
is
Yes, please. I could not hear you.
What is the need of having exciting?
Huh?
Why do we need exciting? Like
XIT is the input for the ith sequence at the tth time step. So xi is a sequence, is one sequence. So we can have, when we are training the network, we can have 100 training examples, x1, x2, x100. So xi is the ith instance, and this instance is a sequence, and xi1, suppose is a sequence of length 4. So we have xi1, xi2, xi3, xi4.
okay.
Is it okay? So xi is the ith instance, and if it has length 300, it will have xi1, xi2 up to xi300.
Okay, ma'am, got it.
Okay. Anybody else has some question?
Ma'am, I have one doubt. Like in RNN, we just have to update, or we just have to take the parameters as W, while in CNN or a fully connected layer, in that if we have two hidden layers, then we have two weight matrices, right? But here we have only one weight
This is a
matrix.
single layer RNN. I'm right now talking about a single layer RNN.
Okay.
Even a single layer RNN, actually it is a very deep network, because the network depth is based on the length of the sequence. Even if it is a single layer RNN, suppose there are 4, sequence length is 4, and you see that the depth of the network is 5. Okay. If you go from x11 to the output, 1, 2, 3, 4, 5. It passes 5 layers for a single layer RNN. Is it okay? A single layer RNN is actually a deep network, and the depth depends on the length of the sequence.
Means we can also have multi-layer RNN. Right?
Yes, you can have. Right now, I'm just showing a single layer. Okay, we'll come to multi-layer.
Ma'am, how are we learning the weight parameter W?
By back propagation?
No, ma'am. When in the first layer, if we learn something, we get some W. Will it update in the at the time?
Yes, it's the same. That is what I said. The same W is used.
So it will be updated.
Yes. When I update this W is also updated, because they are in the same variable, same memory location.
AL is the output, ma'am. after AL is A power L is the output of after each layer.
That is the convention that we are following. Actually, we will replace it by H. Yes, AL is the output of every layer. Every
Okay.
time step, L is the output of this time step, which feeds to the next time step. Right?
Okay.
There are other, this is just one way of. Now we were looking at the input. So far in the previous picture, we did not show the output. Now the output can be at the end, or the output can be in at every time step. Right? There are different configurations of RNN. Now, there can be output can be single or output can be sequential. And if it's sequential, it can be fixed size or variable size. For example, if your task is given an image, generate a textual description, right? So the textual description is a sequence which is variable size. Okay. So this description is a group of people standing around a room with remotes. And this tells a young boy is holding a baseball bat. So this sentence and this sentence, they have different length. Okay. So your output can be variable length or fixed length, or it can be a non-sequence. For example, one configuration of this thing is input and output at every time step. This is not a good example for this. Suppose in the natural language processing, we have a task called part of speech tagging, where the input is a sequence of words, say W1, W2, W3. This W is word 1, word 2, small w, okay, not parameters. Okay. So for every word, we have to tell that this is a determiner, this is a noun, this is an adjective, this is a verb, etc. So we have parameters here. One set of parameters W1, which is shared, which is from input to the hidden layer. Another set of parameters W2 and another set of parameters W3. But all the parameters that I have are shared across time steps. So this is one configuration of RNN. So there can be different ways to use RNN. This is a simple configuration. This is actually not an RNN. You have an input, you have hidden layer, you have output. Standard multi-layer network with a single hidden unit. So there's no sequence in the input, no sequence in the output. So technically it is not an RNN. Then if we look at RNN, users of RNN, the configuration could be one to many. For example, your input is an image, and that image you give as a single input. Maybe there's a CNN, and the last layer of the CNN, there's a vector, which you give as input. And the output is the caption, the textual description of the image. And that is a sequence. So there's a single input, a sequence is an output. Or the configuration can be many to one. For example, input can be a video, which is a sequence of images. The output is the classification of activity. Okay, the activity could be walking or running, sitting. Okay, so this is the classification. This is the many to one configuration. Then in machine translation, we have a sequence of words as input, another sequence of words as output. Suppose you have a Hindi sentence as input, you want to find out its English translation. Now you take the entire Hindi sentence, you process it, and then you output the English sentence. But it is not one-to-one mapping. When you translate from Hindi to English, it is not that every word you separately translate. The English sentence and the Hindi sentence can differ in length, and it will differ in ordering of words. A fourth example is, every stage we have an input and output, like part of speech tagging or frame level video annotation. Input is a sequence of frames in a video, and output is for every frame we have a annotation for that. Maybe the activity in that frame. Okay. So there are different ways in which RNN is used, and what is common is that either there is a sequence in the input, input like here, or a sequence in the output, or a sequence both in the input and the output. Okay. Now let's look at an example task, which is the sentiment classification task. So you have given a review, for example, a restaurant review from Yelp or a movie review from IMDb, and you want to classify this review, whether it is. Yes, you have some query?
Yeah, ma'am, sorry to interrupt. Ma'am, in the last slide, like when we were doing translation, ma'am, I don't know if it's a pertinent question with respect to the class, but ma'am, while we are doing English to Hindi translation, the translation is happening, that's fine. But ma'am, how does the, like, suppose a sentence in English is supposed showing a sentiment of hatred, right? Like when we do translate it to Hindi, how does the sentiment is maintained? Like how does the hatred feeling still comes out in the Hindi translated part as well?
How does the sentiment come out?
Yes, ma'am. Like in the English, suppose there is a hatred. Like in the Hindi translated part, there is also the hatred sense, right, ma'am? Like,
There is what a hatred. You're talking about hatred.
Yes, ma'am.
Huh.
Yes, ma'am. Suppose like whatever feeling is in the English sentence, in the translated Hindi sentence, the feeling is still there, right, ma'am? So how is
right.
that?
Ideally, yes. Ideally, the entire content, entire tone, everything, whatever is there in the text must be there in the output sentence. Yes.
Yes, ma'am. So how is it done, ma'am? Like,
so we will look at, subsequently we will look at some of the models for machine translation. RNNs is a starting point, and specifically for RNN, this type of architecture, which is called the encoder-decoder architecture. That we will discuss. That is one of the models for machine translation. Then we will talk about attention. In this encoder-decoder architecture, we will talk about transformers. All these are used as models for machine translation, and they try to handle this. Okay. So already we talked about in the last class, as a simple example, we talked about word vectors, right? And we said that word vector captures the content of a word. And probably, if, given the surroundings, it can capture the sentiments of the word also. Yes. It's possible, because that's why we don't have a binary vector. We have a, dense vector. It can capture all the, all the conditions under which it occurs, including it should capture the sentiment, hatred, all those things, ideally, right? And we also said that, we have word vectors in multiple languages. We can even put them into the same space, right? So it is possible that, to capture the words in different languages, including all the sentiments, polarities, other syntactic attributes like plurality, gender, all those things, they are part of the word vector. Okay?
Thank you.
There are ways, but, there are various sophisticated models, starting with encoder, decoder, attention, transformer, and all these models we will talk about. Okay, so first we come to a simple task, which is sentiment classification, where you are given a sentence, which from a review, and you want to understand overall, is this a positive sentiment towards the, suppose a restaurant review, is it saying good thing about the restaurant or bad thing? Or a movie review, you take a sentence, is it saying a good thing about the movie or bad thing? So you want to classify your sentence as positive or negative. So input is a sequence of words. It can be one sentence or multiple sentences, but it's a sequence of words. The output is either positive or negative. Or maybe, some cases it is 3-class classification, positive, negative, neutral. So there are some examples. Suppose you say the food was really good. So you want to classify this as positive. And then you have the chicken crossed the road because it was uncooked. It is a negative review of the restaurant. Okay. So your objective is, given the sentence, classify it as positive or negative. Okay. So for example, here in uncooked, that has a negative connotation. right? So this is a very simple network, simple model for sentiment classification, where so X1, X2, X3, X4, we feed in the words of the sentence. The food was good. And this is, instead of A1, A2, we have written as H1, H2, because that is what we conventionally write. So I have the RNN and, so which protects the sequence. And at the last word, it outputs the classification as positive, negative, or neutral. And we can train it if we have a set of sentences in training, which are labeled as positive, negative, neutral, etc. We can train the RNN parameters on this, and then we can take a new sentence and try to find out in the network what is the classification it gives. Okay? And the words can be fed, for example, as a word vector, which we have discussed in the previous class. For the, we have a word vector. Food, we have a word vector. Good, we have a word vector. Is this okay? A second example of a task is image captioning. And I've already discussed the task that given an image, you have to output a sentence which describes the image. And this is an example architecture. You feed the image to a CNN. You have already know about CNN, and CNNs are good at processing images. You take the last layer output of CNN into the RNN, and this RNN only takes input at the first time step, and it outputs the words as a sequence. Right? So we have this RNN, and then at every time step in the output, we have a linear classifier which does multi-class classification. On what? You have, how many classes are there for this classifier? Can you tell me?
The number of words.
Number of words, excellent. So you have V words in your vocabulary. So you have all the words, aardvark, ant, balloon, cat, the, etc. So you have all the words, and it will try to find out which word it should output. So you can have a softmax, some linear network, and then a softmax. So you can find out the probabilities of the different words, and based on that, you can output the word. Okay, so this is a sample architecture for image caption. Now, these are some examples of using some form of RNN and then using the RNN to generate sentence, generate text. So what is done is that you take the, let us say the collected works of William Shakespeare, and you train RNN on that. Now you feed one word or few words to that RNN, initial words. And then you ask the RNN to keep on generating the next words. Okay. And these are some examples of text which was generated by an RNN, which was trained on Shakespeare's corpus. You can read this from the Speech and NLP textbook or from this site. Now, as we said, RNN is good for modeling sequences. A simple sequence we are showing where there's an input sequence, and this is part of the input sequence. This is the tth element of the sequence. This is t minus 1th element, t plus 1th element. And we have ht minus 1, ht plus 1, and this is ht minus 2, this is ht plus 3, etc. So overall, this is the function which this hidden node implements. ht is a function of ht minus 1 and ht. Okay. This says that ht is a function of xt and ht minus 1. And this function has parameters theta. Theta is the set of parameters in the function. Okay. And as we said that we reuse the parameters of theta for every time step. We can compactly represent this RNN like this. This is the input, this is the hidden node, and this hidden node feeds to the hidden node in the next state, And we can denote this by this delay function. Okay? Or we can say, xt is the input. If you have an output also, yt is the output, and ht minus 1 feeds to ht through a one-step delay. So you can use an RNN to predict the future from the past. For example, you can give a part of a text, and then you can ask the RNN to generate the subsequent text. You can use it for generation of text. For example, you are trying to compose your email and you write a few words, and you can ask an RNN to generate the possible next words or next sentences of your email. So the HT that you have got at the time step t, this HT can be thought of as a summary of the previous input. So HT is a summary of the previous input. But summary may not be everything. For example, if you're doing machine translation, you want the summary to capture everything about the previous sentence. If you are doing sentiment classification, you are not really looking at understanding everything, but you want to capture whatever is relevant for identifying sentiment. So we can say HT is a summary of the task relevant aspects of the past sequence of inputs up to T. Okay. This is clear to you? If you have any confusion, please ask. Now, as you have said, what we were showing now in the pictures were single layer RNN. You can also have stacked RNN or multi-layer RNN, where you can have, for example, this is your input sequence. This is the sequence. So as we saw that, based on the sequence length, we have a deep network. We can also have stacked RNN. So we have hidden layer of layer 0, hidden layer 1, hidden layer 2, and so on. Okay. So here we said that these parameters, say W1, are shared. These parameters W2 are shared. If we have 2 layers of RNN layers, we have another parameter W3 here. And we have another set of parameters W4, which go from this connection. And then we have W5, etc. So you can have RNNs which are stacked. If you have multiple layers of RNN, the parameters are different at the different layers of the RNN, right? But within a layer, across time steps, the parameters are shared. Is it clear?
Yes, ma'am.
Ma'am, for 2-layer RNN, what will be the number of weight matrices?
Depends on input-output connections. Here we have input to first layer, right? Then first layer to second layer to output. There are 3 weight matrices. And within the first layer, from one time step to another time step, we have a set of parameters. From second layer also, one time step to another time step. So in this network, we have 5 sets of parameters.
Okay.
So this also shows a 2-layer RNN, which can be compactly represented like this, or which can be unfolded like this. And in this network, this is your input and this is your output. And as you know, the loss is computed. So when you give the input and these parameters are known, then so these are the parameters A, B, etc. And also parameters here. So based on these parameters, you can compute the output, right? And based on the output and the target output, that is the ground truth, you can compute the loss, and based on the loss, you can do backpropagation to learn the parameters of the network. So in order to apply backpropagation, you have to unroll the network given the sequence length. If the sequence is length 10, so you take this thing and you unroll the network up to 10 length sequence, and then on this network you do backpropagation. So this is called backpropagation through time. Okay, so this shows, suppose there's a sequence length of 3. This is how the network is unfolded: x1, x2, x3, and then we have, h1, h2, h3, and then output y1, y2, y3. And based on y1 and the target value y2 and the target value y3 and the target value, you have the losses computed: L1, L2, L3 are the loss. So you can take the total loss to be L1 plus L2 plus L3, and on this loss you can do backpropagation. So this unfolded network, you can treat it as one big feed-forward network that takes in the entire sequence. To this network, the input is x1, x2, x3, output is y1, y2, y3, right? And based on that, you have a loss function. From the loss function, you compute the gradient and do usual backpropagation. And while you are doing backpropagation, you update the shared parameters. Just as you do in CNN, you have shared parameters. Here also you have shared parameters, but the shading is a little different. And then I'm not going into the details of the backpropagation. And while you're doing backpropagation, you start with, suppose this loss you start, and then along the way, you compute the gradient of all of the parameters through the calculus, chain rule, etc. And then based on that, you do backpropagation. And this is called backpropagation through time. And while you are doing backpropagation, this shows that this same W is shared across multiple time steps. And at each time step, when you are updating, so you update W here, and then this W gets updated. You again, update it for this time step. Again, update the same W at the different time steps. So same W is being updated through different time steps. So every path from W to L is a dependency. So the same W, if you consider, this is a length T sequence, this W, while you are backpropagating it, the same W through L1 when you are backpropagating, it occurs once. Through L2, this W occurs twice. Through L3, this W occurs 3 times. The LT plus 1, it occurs T number of times. So I will, I'll stop today. I will carry on tomorrow. So while we are doing backpropagation, we are, this loss, we have, so we have two summations. One is we are summing over the loss L1, L2, L3, L4, L5. And then for every Li, while we are doing the backpropagation, we are following these paths. Right? And these paths traverse the same W multiple times. Okay. So same W is being used across different loss function. For every loss function also, it occurs multiple number of times. And this gives rise to a difficulty that these weights, if you are not being careful, then there is some problem called, gradient diffusion, which we will talk about in the next class. But today I will just end here saying that, backpropagation through time, we forward through the entire sequence to compute loss, then backward through entire sequence to compute gradient. However, if your sequence is very large, for example, if you take the entire text document, then this becomes a little difficult to use, and sometimes you may do truncated backpropagation, where when you're doing backpropagation, instead of backpropagating to the entire sequence, you take a truncated sequence, let us say up to length 10. So you only backpropagate up to a specific length. That is called truncated backpropagation through time. So with this, I will stop today. You may have some questions. So you please be prepared with those questions so that we can take it up in the next class as we, as we finish answering your question. And then we will talk about LSTM, which is a type of RNN, which handles some of the deficiencies of recurrent. Okay.
Thank you, ma'am.
Okay, thank you. So please, if you have